welcome all of you to the organic chemistry class. Today our class is benzene. Benzene is a molecule where we have 6 carbons. Each corner we have 1 carbon, and each carbon is also holding 1 hydrogen. So the molecular formula of this compound is C6H6, but it has one specific arithmetic. See, the double bond, single, double, single, double. 3 double bonds are not at one side, but they are spread over the molecule alternatively. This particular structure will give some stability through the resonance, and consequently it has got a polarity and the other few more points which gives a very excellent stability that leads to give the aromatic nature. So aromatic compounds, aromaticity also we will take in this particular chapter. Now let us go for the how this compound is preparations of this benzene. I just give the gist of this. We have a benzene containing some groups, like if alkyl group is there, let us say any alkyl group, it may be a methyl, ethyl and so on. When you oxidize with the potassium permanganate with the acidic medium or alkaline medium, boil strongly, what happens? The alkyl group, if it is methyl we call toluene, if it is ethyl, ethyl benzene, all will be oxidized to their corresponding carboxylic acid. Though we have a long chain, also will become benzoic acid. Subsequently, what you do is you add some sodium hydroxide, it will become into the sodium salt. The 3 double bonds, you too can write like a ring also, because 3 double bonds going on rotating, and we don't know where exactly the double bond is there, where single bond is there. Now this compound, when you add a solid, this compound sodium benzoate is also a solid, you add sodium hydroxide solid and calcium oxide solid, go on, heat it. The reaction is called fusion, heating solids to get a liquid. Perhaps the first organic compound, because of the melting point, first the sodium benzoate melts and it looks like all the 3 are melting together, but actually the first sodium benzoate melts and all 3 will become into the single liquid form, and immediately the NaO and this part will become into the sodium carbonate, Na2CO3. So actually CO2 is liberated in the base, it forms into a salt, and then the hydrogen comes to the benzene, that is nothing but a benzene is holding 1 hydrogen, means it is nothing but the C6H6. So benzene can be prepared from the all alkyl benzenes can be converted like this. Alkyl benzenes on oxidation. Acyl benzenes also you can convert in this process. If a COR is there, much more easy to oxidize to get the benzoic acid, and subsequently we get it. Second method is if a nitro group is there. Nitro can be converted into the amino group by reduction process. Hydrogen and nickel, tin and HCl and so on. We have 2-3 different varieties of the reagents to get into an amino. It is a reduction. It is a reduction. In this reduction, we are converting nitrobenzene into the aminobenzene. Aminobenzene and treated with the salt sodium nitrite and HCl. These 2 combinedly will generate a OH and N double bond O. This is called a nitrous acid, HNO2. This is unstable acid, but can be easily generated by its salt and the acid. And you have to maintain a very low temperature like 0 to 5 degrees centigrade. Then the reaction leads to give a product called diazonium chloride, benzene diazonium chloride. This on reaction with a reducing agent called H3PO2 in presence of water, this gives the benzene molecule. Okay. So that is the whole group is removed. It is again a reduction of diazonium chloride with the reducing agent is here. It is a unique reagent. I hope the moment H3PO2 you can guess it is used in the reduction of this the diazonium chloride into the benzene. Now similarly we have one more method where if a OH group is there, this can be removed. If a OH is there also can be removed with the help of the zinc, and the zinc takes away this oxygen, it becomes into the zinc oxide, and you will get a reduction of phenol into the hydrogen, that is benzene can be formed. Zinc forms into the zinc oxide. And this is the removal of the OH, removal of the nitro or amino or alkyl or carboxylic acid. Finally, 1, 2, 3, 4, 5 different compounds we are able to convert into their corresponding the original molecule, that is the benzene, can be prepared. These are all conversions sort. In fact, it is not the synthesis of the benzene. In fact, we have some methods where benzene can be prepared other than the benzene containing molecules. Like for example, if you take acetylene molecule, when you pass through the red hot copper tubes, wherein we don't have the benzene in this side, isn't it? Now we are going to make that is a synthesizing. In fact, the smaller 2 carbon units are joined together to get the benzene. It is a process called trimerization cum cyclization. Trimerization may give a open chain compound, but ring is also forming, therefore it is a cyclization. We too can prepare another method, that is a non-aromatic compound like a N-hexane. Straight chain compounds can be treated with the palladium carbon on heating. It drops the hydrogen from the terminal carbons and you will get first cyclohexane. Actually, palladium is used for the reduction of this to this, maybe hydrogen addition process also, but the same reagent palladium for the dehydrogenation also you are using. Carbon takes this hydrogen, becomes into the hydrocarbon, fumes will be removed. A cyclohexane is formed. Then subsequently, if you heat it with the same reagent, you continue the same reagent, then the hydrogen from the side by side is removed, so that the double bonds are now formed into the in the ring. You will get the 3 sets of hydrogens. When you remove, you will get this type of the benzene. Benzene is so stable, so therefore preparation of benzene, it so happens from if the one more carbon is extra, you will get methyl benzene. If 2 carbon this side or that side, if 2 carbons are extra, ethyl benzene or xylenes may be prepared. We have one more industrial method from the carbon. Take the carbon, we are heating it in absence of no oxygen. You are heating strongly, not in presence of the oxygen. If oxygen is there, what happens? Burns into carbon dioxide and the carbon monoxide. That's what we are doing in the rail engine and so on. But here we are heating in presence of the hydrogen. So thereby what happens? The carbon reacts with hydrogen, huge number of useful compounds will be formed. This is called what? Destructive distillation of the coal. This coal we are taking. Coal destructive distillation will give a gaseous product called coal gas. This contains mostly 1 carbon to 4 carbon, the gases of hydrocarbons like methane, ethane, propane, butane and so on will be there. And there is a liquid, this is a gaseous one, okay. 2 liquids are there, 1 solid is also formed. The 2 liquids, the first one liquid is called coal tar. Coal tar. This is the one we are interested in. This coal tar, we have a huge amount of the benzene. And we have a ammonical liquor, and then the unconverted the carbon will be resulted as a coke. This is a solid particle, okay. So from these 2 liquids, one is aqueous, the other one is organic, so it floats, one floats on the other one. The coal tar and further distillation, you will get the different types of the light oil, heavy oil and so on. And this light oil and further distillation, you will get 90% benzol. And this benzol on further distillation, you will get crude benzene. These are all now, only the reaction is only in the first stage, carbon reacting with hydrogen. When once the coal tar is formed, what we are doing is only just heating, separating the compounds into the fractions based on the boiling point difference. The light oil will give 90% benzol and then crude benzene, and then once again if you crystallize, if you further distillation will give the pure benzene. Okay, we have some commercial the aspects and all that, but this is one method where we can rely on this industrial method, or the manufacture of the benzene can be from this the coal we can relay. This is a commercial method in fact. Now let us go for some of the properties of this benzene. Before going to the properties of the benzene, benzene has got one unusual behavior, that is stability. Let us have one point regarding the stability. We have seen in the last in the fundamentals, whenever a double bond and a double bond is in conjugation, or the pi bond and a charge, the charge can be plus minus a dot, a pi bond and a pair of electrons like X with a lone pair. These are all leads to the resonance. Resonating molecules will acquire the low potential energy and the stability. So the benzene also has got this type of the fundamental requirement. What is that? Resonance stability is there. So it has one special feature. What is that? Conjugation is there. In addition to the conjugation, it has a few more points. What is the next one? Is all the carbons happens to be a sp2 hybridized carbon. This carbon, if you take it, is a sp2 carbon. That means all these carbons and hydrogen is in one plane. In fact, if you throw this molecule, all the 6 carbons and 6 hydrogen will touch the ground. That means the entire molecule is planar. So this type of planarity is the additional quality. So the whole molecule is in plane. So therefore, this is the second feature. The third feature is it has a ring nature, cyclic nature. Okay, the ring nature is there. Fourth feature is it has a set number of pi electrons. What is that set number? 4n plus 2 number of pi electrons. What is this n? N is a just number like starting with 0, 1, 2, 3 and so on. This is a full number, int number. It cannot be a fraction. It can be 0 also. If it is n is that is 0, 0 into 4 is 0, 0 plus 2 is 2 electrons. 2 pi electron system is aromatic. Okay. So when all these 4 conditions are fulfilled, there comes one special stability. Conjugation gives stability, okay, but conjugation in addition to these 3 special points is going to give some special stability. Special stability is nothing but the aromaticity we can design. Okay, aromatic nature means the compounds have got some utmost stability. Due to this stability, this double bond feature, the double bond has to undergo what type of reaction? Addition reaction. That addition we are not finding at all. Okay. So aromatic character we are going to define, but whenever this extraordinary stability is coming, this aromatic nature is coming. So a scientist called Huckel defined a rule. Whenever a molecule contains conjugation planarity cyclic with this set number of pi electrons, the compounds will attain some special stability, is nothing but the aromatic nature he defined. However, the meaning of aromatic nature is different. When which molecules are aromatic means he defined under these conditions molecule will become aromatic. But what is aromatic? Define aromatic means not these rules. Aromaticity is whenever compound has a double bonds in the structure, but the double bonds are not showing the properties of double bonds. We have seen in the alkene chapter already, double bonds are going to show the addition reactions, ready to addition undergo, ready to oxidation, ready to polymerization, right? These are the characteristic reactions of alkenes. Whenever there is a double bond, these 3 should be the special reactions. But the benzene not showing all these 3 reactions. That means in spite of having the double bond, the benzene will not show. But in addition to that, alkane molecules like ethane and methane would like to undergo replacement. For example, if you add chlorine, one chlorine replace. This is called what? Substitution. So substitution reactions it is showing. All these 3 reactions it is not showing. So instead of showing the ene reactions, it is showing a characteristic reaction of alkane, which is a saturated compound. So now the definition of aromaticity is a special behavior whenever a molecule is containing double bond, but in spite of the double bond it is not showing the characteristic reaction of alkenes. Instead, it is preferring to show the reactions of saturated alkanes property, that is substitution. Such a property is defined as a aromatic. Benzene also, for example, if you add chlorine, instead of adding, what is happening? The benzene undergoes one hydrogen replacement. 3 double bonds will be restored as it is. One H and one Cl get out as a HCl. This is nothing but a substitution reaction. However, we will see later what type of mechanism means Cl plus is substituting. Therefore, it is called a electrophilic substitution reaction. So, the benzene undergoes a special reaction called a electrophilic substitution. But 2 points be clear: which molecules are aromatic means Huckel defined under these 4 conditions are aromatic. Second, what is aromaticity means a compounds though contain double bond, they are not behaving like alkenes but behaving like alkanes and showing a substitution reaction. Such a property or abnormal behavior or unusual behavior is called aromatic property. Now, let us go to some examples of the aromatic compounds. One example already we have taken, a benzene molecule, but when 4n plus 2 condition, where n is equals to 0, that means 4 into 0 plus 2 means 2 pi electrons. 2 pi electron containing compound provided 1, 2, 3 conditions are fulfilled. That is, a molecule like there are only 3 carbons are there, 1 double bond and a carbocation if it is there. Now, it is fulfilling all the 4 conditions. What is that? It is cyclic, it is planar. There is 1 hydrogen, okay, all the carbons are sp2 hybridized, planar, and conjugation is there. What conjugation? Pi charge conjugation, this side or that side pi charge. The whole molecule is in the conjugation, cyclic, planar, and the number of electrons are n is equals to 0, 2 pi electrons. There is a pi bond in which 2 pi electrons are there. Therefore, it is aromatic. What is aromatic character means? If you add chlorine, no addition. Right? Instead, if you add chlorine in presence of a catalyst like anhydrous ferric chloride, what is going to happen? The double bond will be there, but one of the hydrogen will get replaced. Right? One of the hydrogen get replaced. In fact, the charge and double bond goes on changes. Where is the double bond and the charge means? In the structure it is on the top, but it can be, if the double bond is moved here, it comes to this place. Okay, if the double bond is moved like this, it comes to the other place. So, at somewhere the double bond and the charge is going on changing. Therefore, all the 3 resonating structures can be summed up and written as a double bond is going on rotating, and the positive charge is also not at fixed one position. It may be shown at the center. Okay, and this it's not a molecule, it is an ion. Some anion will be outside, okay, chloride or hydroxide and so on, some anion will be outside. This piece is called cyclopropenyl, cyclopropenyl cation. So, the examination I will give which of the following is aromatic means, if it is there, you say it is aromatic. What is the nature of the aromatic? It will not undergo addition or oxidation or the polymerization, but it undergoes substitution. Just like when chlorine is there, one hydrogen will go and the chlorine will come. Okay. So, this type of properties, when n is equals to 1, 4 into 1 plus 2, that means 6 4 into 1, 4 plus 2, 6 pi electrons. See the examples, now the regular example is benzene, and like that there is an oxygen with a pair you include 2 plus 2 plus 2, one pair is there, but outside don't count, and this is furan, okay, and there is a molecule like pyron with nitrogen, a pair, okay, pyron, and thiophene with the sulfur with a pair. The outside pair don't count, only inside. The pair which is involved in the resonance rotating is counted as a pi electrons. So, these are all aromatic. In addition to that, there can be a charged pieces like a carbon with one hydrogen with a negative charge. The negative comes here, the double bond goes, that is the negative charge goes here and here and here and here. It goes on rotating. So, what is the resonance hybrid of this charged structure means? We have a 5 carbons, we don't know where exactly the double bond, so therefore, they show like this, or you can show just simply round, okay, but this round should be, this circle should be as far as closer to the single bond, and it should not touch to the single bonds, and there is a positive charge spread, that minus charge spread over all the 5 carbons, better put it in the center. So this is called what? Resonance hybrid structure of this particular piece. How do you call this one? It is a cyclo 5 carbons pent, 2 enes are there, diene. It's a cation, therefore aryl anion. Cyclopent A will be added extra to have a soft pronunciation. Therefore, according to the systematic nomenclature, it is called cyclopentadienyl anion. Outside, some cation will be there, Sc cation, sodium or some cation will be there, but the whole molecule, the anion is aromatic. I am saying this anion is aromatic. Okay. Now, similar the way you can also have a cation like 7 carbons are there, 1, 2, 3, 4, 5, 6, 7 carbons are there. 3 double bonds are alternatively, and the 1 carbon we have a positive charge. Positive charge means 1 electron is missing. So 3 into 2 is 6 electrons are there. This is called hept. 7 carbon means hept. Cyclohepta trienyl cation is also aromatic. Okay. So similarly, when n is equals to 2, 4 into 2, 8 plus 2, 10 pi electrons is aromatic, for which you can take a 2 benzene system like a naphthalene molecule and so on, anthracene for the n is equals to 3 and so on. You can take a number of examples. Okay. But only thing is the n cannot be a fraction. It can be 0 also, but not the. Actually, the Huckel dealt with only 1 cycle ringed compound. Later, it is extended to the 3 members and 4 members and so on. But as per the Huckel's rule, if all these 4 points are the fulfilled cyclic conjugated planarity with a set number of electrons, that is 4n plus 2 system, he said it is it's going to show some extraordinary stability. That's called aromatic nature. Now let's go to the classical properties of this benzene. Benzene undergoes 3 types of property. One is electrophilic substitution reaction. One is electrophilic substitution reaction, in which we have a chlorination or halogenation. You can take halogenation, introduction of a halogen. Examples: chlorine, bromine is the best examples there, and alkylation, acylation, nitration, introduction of the NO2 group, introduction of OCOR group, introduction of R group, and the 5th one is sulfonation, introduction of SO3H group. So halogenation, alkylation. In all this, one of the hydrogen is get replaced with halogen or alkyl and so on. These are all substitution basically, and they are undergoing a with electrophile it is substituting, therefore it is the electrophilic substitution reaction. Halogenation or chlorination we take and we take the details of this mechanism. Reaction mechanism, let us say, overall reaction is represented as a benzene when treated with a chlorine molecule in presence of a anhydrous ferric chloride, heated slightly, what you get is benzene becomes a benzene with chlorine, chlorobenzene, and one H and Cl gets out as a HCl. So the product is chlorobenzene. For this reaction, we are going to write the mechanism of the reaction. In this mechanism, a few points you have to note here. Even in absence of ferric chloride, also the reaction takes place. Ferric chloride is considered as a catalyst. Catalyst by definition will not start the reaction, but it augments or increases or hasten up the reaction condition. So therefore, the role of ferric chloride, why it is increasing, let us see here. In the first stage, what is happening? The chlorine molecule is reacting with this anhydrous ferric chloride. Anhydrous means you take a common ferric chloride, will contain some hydrated H2O, heat it strongly beyond 100, the moisture will go out. So-called ferric chloride is nothing but the anhydrous ferric chloride. That ferric chloride you add it to heat and slightly heat it. The ferric chloride will take the Cl minus and becomes into the Cl plus, and the rest will become into the FeCl for minus. Now, what is the role of ferric chloride? It holds this minus party, heterolytic fission, this minus party it holds becomes into FeCl3, and there will be a small attraction between the cation and the anion. Ready-made Cl plus is rare. If it is not there, Cl2 must come and break and get the Cl plus, isn't it? So, the breakage has become easy in presence of the ferric chloride. Now, take the second stage. This is not the steps, actual step will be like this. When benzene is there, you take the Cl plus on the arrow, show that it is going to come closer. As the chlorine comes closer and closer, the electron cloud in the benzene attracts. A stable intermediate is formed, that is called a pi complex, also you can show it. But as the chlorine comes, the pi bond either this side or that side polarizes. This step is called a polarization. So, polarization of the benzene leads to give the negative charge and a positive charge is formed, remaining 2 hydrogen, show it like this. Then the Cl plus is going to react with this Cl minus. Either way is correct, minus attacking on the plus or plus attacking on the minus, both are correct, but it is technically the 2 electrons from the benzene flowing towards the Cl, therefore, show the arrow from minus to the plus. Plus is nothing. So, something flows into the nothing. So, therefore, minus is attacking on the plus, and there comes a bond formation. This will become now the step 1. So, by definition, after step 1 what you get is called intermediate species. So, what is the intermediate species in the halogenation means there will be a chlorine here, and on the next carbon, either this side or that side, there will be a positive charge that is known as what? A carbocation, and this species is called a intermediate species, which is having a plus charge on the carbon, therefore, we call carbocation. So, question may be asked, which of the following reactions passes through carbocation? All electrophilic substitution reactions passes through the carbocation. Then what happens? Now, see here, this molecule, this intermediate piece is not having the aromatic nature, only 2 pi bonds, that means 4 electrons only. So, therefore, in order to get the aromatic nature, the hydrogen is dropped, the 2 electrons will come back and a double bond is formed. So, therefore, finally, what happens? A third double bond is reconstructed in order to what? Get once again aromatic nature. So, the hydrogen will be shown out. Now, with that we are going to show the third step. That means, the H plus will react with the charged FeCl4 minus, again forms an hydrous ferric chloride back. This is catalyst formation, and the H and Cl is the byproduct formation we are showing. But what are exactly the step 1 and step 2? Step 1 is electrophile attacking on the benzene, and the hydrogen removal happens to be the step 2. This is step 2. Isn't it? Step 1 is electrophile attacking, and hydrogen removal getting the product is the step 2. However, I have shown this in the 3 stages. First stage is how the electrophile is formed. The last stage is how the catalyst and the byproduct is formed. The main reaction, actually 4 steps are the 4 stages I am showing once again. This first one, initially benzene is shown to polarize in presence of the chlorine, then the chlorine attacks, that is the step 1, intermediate carbocation, and the dropping of this hydrogen, and then you get this chlorine. In fact, you can also have one question here. If a Cl minus attacks here, what happens? So, just see. 1 chlorine is added, 1 chlorine is added. This happens to be an addition reaction. This addition never takes place, because if the addition takes place, 1 double bond is lost. So, how many double bonds are there? How many pi electrons are required to get this special stability? 6 pi electrons. That is it's a non-aromatic compound, we will say. Non-aromatic compound. Non-aromatic compounds are less stable with a more potential energy. Therefore, the intermediate has 2 chances, going to the stable product, going to the unstable product. Naturally, it drives to the stable. That is why a question like, why after attacking the Cl plus, why not second step will be the addition? If the addition followed by addition means net reaction will be an electrophilic addition. That never takes place, because the product is a unstable one. Similar the way, instead of the Cl, if you take this is the CH3. See, the final product will become a methyl benzene. That is exactly the mechanism for the Friedel-Crafts alkylation, that is methylation reaction. If instead of CH3, if you take a CH3COCl, the Cl will be dropped and this will be the attacking piece. This is called acetyl carbocation. It will become a Friedel-Crafts acylation reaction. Similar to that, if a nitration reaction, nitric acid and sulfuric acid is taken as a catalyst, NO2 will be the attacking species. Nitric acid in presence of sulfuric acid. If you take concentrated sulfuric acid, this donates a H plus and goes attacks on this one and becomes into water. The NO2 is generated as a NO2 plus. This is what attacking species in the nitration reaction. So, question may be asked, what will be the attacking species in the nitration NO2 plus? What is the attacking species in the chlorination? Cl plus. Alkylation R plus. Acylation or CO plus, nitration NO2 plus. Rest will become H2O with the two molecules. If you take, it will become the H3O plus, okay, and plus HSO4 minus. So, the H liberated from the benzene goes to here and forms H2SO4, but net will be the attacking will be this one. Again, the catalyst is sulfuric acid. This supplies a proton so that water comes out and NO2 is generated, right. In the sulfonation, sulfuric acid acts as catalyst as well as the reagent. One more sulfuric acid you take. One sulfuric acid donates a proton and becomes into water. With the help of the proton, it will become into H3O plus, right. This is not the attacking species. What is left over is called a SO3 neutral molecule. As I said, electrophile will be three types. All cations are electrophiles. All molecules containing vacant orbitals are electrophile. This is the third type of electrophile where hetero type of bond is there which polarizes into plus minus. This is called potential cation, which acts as an electrophile, attacks on the benzene. So, in the sulfonation we have a SO3 molecule. Generally in all the electrophilic substitution, electrophile happens to be a plus charge. But in this case, electrophile is neutral molecule. Only the sulfonation we have a neutral electrophile attacking, and however, finally the one H from the benzene it takes and will become to HSO4 group. Therefore, sulfonic acid is generated. In all these reactions, there is a lot of similarity in the mechanism with a small change. If you can grasp it, you can follow any one of the reaction you can write down. Then we have the addition reactions. In the addition reactions, generally as I said, the benzene hesitate or will not undergo addition. No fair addition reaction. Addition will not take. But under some conditions, like if you take chlorine and UV light, okay, UV light, irradiation with the UV light, the chlorine breaks up into dot and dot. These two dots will be goes on adding, you will get a hexachlorobenzene. Hexachlorobenzene. And each one hydrogen also will be there, isn't it? So, 1, 2, 3, 4, 5, 6 hexachlorobenzene is formed. This is also called benzene hexachloride. Benzene hexachloride, BHC. It is commercially, it is a insecticide also known as gamexane. It has some conformational, the isomers. One of the conformational isomer, gamma isomer, is a powerful insecticide known as gamexane. Okay, lindane, gamexane, 666. Its formula is C6H6 and Cl6, 666, and so on. Some common names are there, but this halogenated addition reaction it is. Similarly, if you add hydrogen in presence of nickel and high temperature, 3 moles will be added, you will get a cyclohexane. These are all rare reactions, however, but under forced condition, some addition reactions takes place. The third, similarly, oxidation reaction. The benzene, again, if you do oxidation, it will resist for the oxidation. Even with the permanganate, dichromate, boiling with the acid or base, it will resist. But if a compound contains some alkyl group, as we have seen in the preparation, the group can be oxidized readily, becoming to the COOH. But the benzene ring resists the oxidation reaction. But there are some reactions like if you do ozonolysis. Ozonolysis means and the triple bond the O3 will be added, rearranges to be ozonide. How many ozones are consumed? Question may be asked, because 3 double bonds are there. 3 ozones are consumed, you will get a triogenide. Triogenide. This triogenide, when you hydrolyze with water in presence of zinc, you will get a 3 pieces. Each piece, this, let us say this is the piece number 1 I am writing, a carbon with carbon single bond, hydrogen and hydrogen. The double bond will cut into double bond O and double bond O. This is nothing but the glyoxal. How many glyoxal molecules are formed? 1, 2, 3. So, therefore, 3 ozone molecules are consumed. The intermediate is a triogenide and the product is 3 molecules of glyoxal is formed. If a methyl is there, then you will get a methyl glyoxal and so on. The substituted, we have some points regarding the how many pieces are formed, how many alkyl groups are there, and all that also can be questioned. But the overall is it gives a triogenide and becomes into 3 pieces. These 3 pieces are nothing but the glyoxal. Okay, right. Now let's go to the some questions of the benzene which were asked previously and also expected questions. Next, first question. The first question is benzene with O3, X is formed, with zinc dust Y is formed. As we have seen on the board, the ozenide is a triogenide, followed by it gives the glyoxal, that is 3 molecules of glyoxal. Answer goes to the third question, 3. Next. In which of the following ortho-para substitution by an electrophile is very facile? So, for this I have to take little 1 or 2 points I will explain here. If benzene contains groups like OH, similar to the OH, okay, similar to the OH, I am introducing a electrophile. Where goes the electrophile? It has the 2 chances, 3 chances, ortho, either this side or that side is called ortho, either this side or that side is called meta, and this center is called para. So, 4th position to the OH is para, 2nd position ortho, 3rd position meta. So, if electrophile can go to the one of these 3, but phenol is a group which shows resonance with the phenol. The effect is called plus mesomeric effect. Due to that, the pi bond is polarized to the ortho, followed by, if the minus is given, this to para and goes to the para. That means in the resonance structures you find negative charge only at ortho, para and ortho. Therefore, electrophile also goes to the ortho electrophile, that is nitration, halogenation, bromination. For example, phenol gives a tribromo product at a time. That is all the 3 ortho, para will be filled. If you control it, 1 bromine goes to the. So, either at ortho or at para, okay, depending upon the nature, or at ortho, para and meta, the ortho, para, ortho, isn't it? So, all the 2 orthos and para, a tri-substituted products also may be formed. But the point is very clear that the electrophile will not go to the meta, because at meta position there is no minus charge formed, therefore, the plus charge is not attracted. Okay. So, all the groups means the OH are similar groups which shows plus some effect. Okay. OH or OR, this is called alkoxy, okay, and OCOR, that is acetylated phenol and alkylated phenols, acylated phenols, and then amino group, aniline, or alkylated amines, dialkylated amines and acylated amines, and HCOR. So, what are the groups? Hydroxy, alkoxy, acetoxy, amino, monoalkylated, dialkylated, acetylated. In addition to that, halogens also. Halogens also will have a lone pair. What is the identification mark here? All the groups which have got a group, attachment group has got a lone pair, shows plasma effect, directs to the orthopara. That is the similarity in all these groups. Okay, all this directs to the orthopara. But the halogen has one exception. This is also orthopara, isn't it? But all these groups increases the negative charge, therefore, the reaction will become easy. So, we are observing the 2 points. One is orthopara directing property, other one is easy. This easy property is called ring activating property. Ring activating property. So, the hydroxy group shows plasma effect and makes the incoming group to go ortho and para. Simultaneously it activates, that means phenol and benzene, which undergoes faster nitration, phenol, because activating group is there. Okay, any one of the group, if it is there, it is a ring activation takes place. But except the halogen, halogen shows ortho para but ring deactivating group, right? In addition to that, even the methyl shows, methyl group is due to the hyperconjugation, it shows the activation, plus hyperconjugation is the reason. Okay, we have seen in the hyperconjugation application how the toluene goes ortho para, the chlorination and so on. Now, the another type of groups are nitro or aldehyde type of groups. If a benzaldehyde is nitrated, okay, that is electrophilic substitution, if you do it, you see the mechanism, that is the polarization, double bond pulls that side, benzene electrons will come, at ortho you will get positive, at meta and ortho you will get positive. So, under this condition, electrophile cannot go to the plus, it like to go to the meta. Therefore, what happens? Meta substituted products will be formed, right? So, therefore, a benzaldehyde are groups which are similar to this one. What is the similarity? All these groups which shows minus M effect. What are the groups examples? Means aldehyde group, right? And a keto group, this is called keto group, and acid group, okay, COOH acid group, and the derivatives of the acids like Y substituted acids, that is acid halides, acid amides, acid esters, and acid anhydride, all these acids, and simultaneously cyanides, nitro and sulfonic acids, and so on. All this which have got the heterotype of multiple bond, the polarization will be outside, so that the benzene electrons are vacated from the ring to the outside. So, the benzene goes into the positive charges, electrophile is also positive, therefore, it cannot go to the ortho para, it goes to the meta. And the rate of reaction also difficulty. So, we have a common point here, all the minus M groups shows meta directing property as well as what? Ring deactivating. So, whenever the 4 or 5 groups are there, you have to identify which group shows a plus M effect, which group shows minus M effect. All the plus M groups ortho para and activating. All the minus M groups meta directing and ring deactivating, except halogens. Halogens shows ortho para but deactivation, and the methyl shows ring activation ortho para character through, not through mesomeric effect but the hyperconjugation. Now, come to the question, in which of the following ortho para substitution by an electrophile is very facile? So, the nitrobenzene NO2 is a minus M group, phenol plus M group, benzoic acid minus M group, acetophenone acetylated group, that is again minus M. So, only the phenol which has got the plus M group, therefore, it goes to the ortho para. Next, reaction will become fast, ortho para and also fast. The compound prepared by the substitution reaction of benzene is a acetophenone, that is a Friedel-Crafts acetylation reaction, we get acetophenone. The others are oxidation and halogenation addition reaction, hexabromide also addition reaction. Next, match the following columns. Benzene is a mixed topics are there. However, the benzene is there. Benzene has got 4n plus 2 pi electrons, that is option 1. If you take A becomes 4n plus 2, that is aromaticity, and ethylene B goes to the 3, that is it has a mustard gas, means if you add sulfur monochloride, you will get a sulfur containing a chlorinated product, that is called mustard gas. Acetaldehyde shows a haloform reaction, silver mirror here, a tolerance reagent when you add silver mirror. Chloroform undergoes hydrolysis, it is oxidation reaction, phosgene formation is given here. So, therefore, the fourth one is the answer goes to the 1. Fourth one answer goes to the 1. Next, what is the molecular formula of the product formed when benzene is treated with ethyl chloride in presence of anhydrous aluminum chloride? This is a Friedel-Crafts reaction. So, benzene will become a ethyl benzene whose formula is a 6 carbon plus 2 more carbons, C8H10. C8H10. That is the benzene when you treat it with ethyl chloride. Benzene hydrogen is replaced by the ethyl group. isn't it? In presence of triple-capped anhydrous aluminum chloride, if you add aluminum chloride will take away the Cl, ethyl group is introduced, therefore benzene becomes into ethyl benzene, whose formula will be C8, H will be the 4 plus again 3 7 plus 2 8, C8 H8 will be the formula. So the answer 1 will be the answer. Any problem? Next, sixth question. Which one of the following is used in the preparation of styrene? Styrene is a polymer prepared out of a benzene derivative. Benzene, when containing a ethyl group, vinyl group, double bonded group, this is known as actually styrene. This is known as styrene. So from benzene you can prepare this compound by taking the benzene and getting into a ethylation, subsequently ethyl chloride and so on, monochlorination, removal of the Cl, a double bond is created and so on. You can touch the starting material is questioning from where you prepare styrene. So styrene and polymerization gives a polystyrene, a polymer, you might have known it. So the answer is 4, that is benzene is the right answer. From benzene we can start and prepare the styrene, followed by you can prepare a polystyrene. Next, the reagent that converts benzene diazonium chloride into benzene. This is the unique reagent, as I said, it is a reduction reaction using the H3PO2, in which a P has got a +1 oxidation state, lower oxidation states of phosphorus is a reducing agent, you can remember here. +1, when you add this water, it will become H3PO3, wherein the +1 becomes into +3 and then a liberated hydrogen is reducing the diazonium chloride into the benzene. Next, fusion with soda lime is used to prepare benzene from a sodium salt of the benzoic acid. That is third, the answer is given wrongly. Answer is 3 actually. The benzoic acid, when you use this fusion reaction, sodium benzoate will give the benzene. Answer is wrong here given. Next, which of the following is the trimerized and cyclized when passed through the red hot copper tubes? The acetylene undergoes trimerization in the acetylene chapter also. This is the one going important question. Here the acetylenes trimerizes. If there is a methyl group attached, we will get a trimethyl benzene, not one methyl, trimethyl, because each acetylene contains one methyl. So 3 acetylenes are used, therefore trimethyl, 1,3,5 trimethyl benzene is known as mesitylene. So mesitylene also can be prepared in the similar reaction by trimerization cum cyclization. The answer goes to the 2 here. Next, according to the Huckel's rule, which one of the following is not necessary to exhibit aromaticity? I said cyclic, plenarity, conjugation and 4n plus 2 pi electrons are needed. Here it is 4n number. That's wrong. 4n number gives actually anti-aromatic nature, that is against to the aromatic nature. The compounds will become highly unstable and very highly reactive compounds. So here the last one is not the correct one. First 3 are necessary conditions. Next, among the following not aromatic compound, the first one has a pyrrole, that is known as, and the nitrogen we have a pair, so 2 pi bonds and a pair on the nitrogen, 3 cyclizes just similar to the benzene. Second one is a benzene. Third one is a 4 pi electrons with a positive charge, that is an anti-aromatic or a not aromatic compound. Fourth one again it is a aromatic because 6 pi electrons are there. As I said, that is known as cycloheptatrinyl cation. Fourth answer is aromatic. Third one is a cyclopentadienyl cation is not aromatic. If it is anion is there, it would have become a aromatic compound. So answer is 3 therefore. Next, characteristic reaction of benzene is, benzene undergoes electrophilic substitution. As we have seen, it is a part of the component in the describing the aromatic nature. Aromatic nature is compounds have got the structure similar to the alkenes, but shows the properties of alkanes, that is, in spite of having the double bonds in the structure, they resist the addition, polymerization, oxidation, but go for the substitution reaction, that is called actually the character, that is unusual character is known as aromatic nature. Next, which of the following group present in benzene directs incoming group to ortho and para and in a nitration reaction. The nitration reaction, why it is given means we have to define what reaction you are doing. In fact, some of the ortho-para directing groups becomes meta-directing when the reaction is altered into nucleophilic substitution. So, therefore, a specific reaction nitration is mentioned because nitration is an electrophilic substitution. Instead of telling electrophilic substitution, he said nitration reaction. So, therefore, towards the nitration, the nitro group is meta-directing, sulfonic minus M meta-directing, methyl is plus hyperconjugation, therefore, ortho-para directing. Acetyl is again a CO group, that is a minus M group. So, therefore, answer is 3. Next. In which of the following reaction neutral electrophile will be the attacking species? We have seen just now chlorination is Cl plus, nitration is NO2 plus, sulfonation is the one SO3 neutral molecule will be there. In the acylation RCO plus, Friedel-Crafts acylation or alkylation R plus and RCO will be there. So, therefore, only the third answer will be the right one, sulfonation. SO3 neutral molecule is the attacking species. Next. Gamexane, a powerful insecticide, is prepared from benzene by. Gamexane is a, I said 6 chlorines containing benzene molecule. Benzene can be substitution reaction also, you can prepare, it is called hexachlorobenzene. But here it is the addition reaction. All the double bonds will receive, every double bond 2 chlorines, therefore 6 chlorines in addition with 6 hydrogens. If 6 hydrogens are replaced, that is an aromatic compound. But here in the addition reaction taking place, 6 chlorines and 6 hydrogens will give a benzene hexachloride addition nomenclature. Actually 6 chlorines, 6 hydrogens, a saturated compound is known as one of the gamma isomer is found to be insecticide, is known as gamexane. Recently, the government banned this compound because of the huge amount of gamexane usage led to a that is ecological imbalance. Therefore, the gamexane is a banned compound right now. So, that is a chlorination reaction will get this benzene gamexane. Next. In which of the reaction, as the number of groups introduced into the benzene, the rate of the reaction is accelerated. The rate of the reaction means here, and that is ring activating groups. Okay. So, Friedel-Crafts acylation is a minus M group, no use. Nitration minus M group, no use. Friedel-Crafts alkylation, it is a plus hyperconjugation. As the alkylation, if you do, first alkylation will be the normal reaction, but the second alkylation, the first alkyl introduced into the ring will help for the second alkyl. 2 alkylation, when you are introducing third alkyl, the reaction will become much more faster. So, therefore, rate of reaction will be the much more faster reaction. Therefore, rate of reaction will be the much more easy. As the Friedel-Crafts alkylation goes on, the alkyl groups introduced into the ring will promote the reaction, that is called acceleration. Acceleration means by second the rate, the speed goes on increases, that is. In fact, Friedel-Crafts acylation is going to be retarded. Nitration, acylation, step by step the reaction will become tough reaction. First nitration at 60-70 degrees, second nitration it is 100 degrees. Why means introduced nitro group will oppose the electrophilic substitution because of the minus M group. So, therefore, Friedel-Crafts acylation, nitration, sulfonation, step by step will become retardation, rate will become diminished in fact. But in alkylation, rate goes on increases. This is a wonderful point, you can note it. Next. The further nitration of nitrobenzene. Nitro is a minus M group, so it goes to the meta-directing group and ring activating. So, therefore, meta-nitrobenzene will be the right answer, isn't it? Meta-nitro means one nitro already there. Second nitro goes to the third position, the 1-3 relation comes meta-dinitrobenzene. Meta-nitro or meta-dinitrobenzene, nothing but same, meta-nitro, nitrobenzene is formed. That is because of the meta-directing property. I think that is the last one. So, we have here the benzene topic happens to be one important topic in which aromatic nature is the one important, that is on which also we are getting the questions based on Huckel's rule, and the benzene shows this electrophilic substitution, especially Friedel-Crafts alkylation, acylation, name reactions. Both alkylation of the benzene and acylation of the benzene is introduced by a scientist called Friedel and Crafts. So by name of honoring them, we have given a Friedel-Crafts alkylation and acylation. The mechanism will be very much similar. The alkyl plus and the acyl plus in the place of Cl plus will get it, and both the reactions leads to give the alkyl benzenes preparation and acyl benzenes, that is aromatic ketones preparation can be achieved. And the benzene preparation, commercial benzene, however, by the destructive distillation of the coal, but any group which is there in the benzene, if you can remove it, we will get the benzene, isn't it? So some methods of the benzene and the aromaticity in the benzene, electrophilic substitution, ring activation, ring that is orthopara directing properties are the some important questions in the benzene. Thank you.